Hello, this is Dr. Amudapriya, Associate Professor Triply from Rohini College of Engineering and Technology, Palkulam, and this is the course Power System Analysis. Here we deal with the swing equation. First, let us see about the stability analysis and the need for stability analysis. Let us start with the term stability. What is stability? The tendency of a power system to develop the restoring forces equal to or greater than the disturbing forces to maintain the state of equilibrium is known as stability. Why we are discussing about stability and what is the need for stability? Obviously, when a system is getting into a trouble due to the problem occurrence, due to the fault occurrence, it has to regain to its normal condition as soon as the fault has been occurred. With the fault occurrence, it has to get cleared of the fault and then it has to regain to its original or the normal condition. That state of equilibrium is known as stability. The ability to keep the machines in synchronism with one another is known as stability. So what are the different types of stabilities? They are steady state stability, dynamic stability and transient stability. Steady state stability is the ability of the power system to regain synchronism after small and slow disturbances like gradual power changes. While considering the dynamic stability, the ability of the power system to regain synchronism after small disturbances occurring for a long time, like changes in the turbine speed, change in load, etc. While transient stability, this concept it is concerned with the sudden and large changes in the network conditions, that is the sudden changes in the application or removal of loads, adding and removal of loads, line switching, line faults, loss of excitation, etc. With this classification, let us see about the steady state limit. It is a maximum power that can be transferred without the system become unstable when the load is being increased gradually under the steady state conditions. What is transient limit is, it is a maximum power that can be transferred without the system becoming unstable with the stability when a sudden or large disturbance occurs. It is not a steady state condition. Let us see about the swing equation of a single machine infinite bus system. The equation which is governing the motion of the rotor of a synchronous machine, this is nothing but a mechanical system, which is a mechanical rotational system consisting of the torque TA, accelerating torque, which is being equal to the J, moment of inertia, into d square theta m by dt square. Theta m is nothing but the displacement of the rotor, the angle through which it is getting displaced. We can consider the accelerating torque TA to be the difference of the mechanical torque and the electrical torque. Then theta m is equal to omega stm, which is a velocity into t plus del m. This is the angle, and then we have to differentiate it, and then we'll be when double differentiation is being carried out, second derivative of theta m gives d square theta m by dt square is equal to d square del m by dt square. Therefore, j omega m d square del m by dt square is equal to PA is equal to PM minus PE, where PM is the shaft power which is given as input to the machine, PE is the electrical power, and PA is the accelerating power. Therefore, also we know that j omega m is equal to capital M. Capital M is the mass. So, M into d square del m by dt square is equal to PA, where M is equal to 2hs machine divided by omega sm, where h is a machine inertia constant and s is nothing but the active power. Therefore, equating this on that, we get this equation, and after that we can have omega s to be 2 pi f. It's an angular velocity, so it is 2 pi f. While considering the 2 pi f, 2 get cancelled, and instead of f you can have f0. Therefore, d square del by dt square is equal to pi f0 by h into Pm minus P2 max into sin del, which is equal to pi f0 by h into Pa. This sin del has been included as an electrical angle and omega s is also an electrical radian mode. Therefore, upon integrating, we can have d del by dt is equal to del omega, and d omega by dt is equal to pi f0 by h into Pa, the above equation, which is equal to d square del by dt square. Regarding the swing equation of the multi-machine system, S machine is the machine rating and S system is the system base. Here we are going to deal with the per unit system. So H system is equal to H machine into S machine by S system. This is the value which we are going to consider. Therefore, H system by pi f into d square del by dt square is equal to Pa, which is Pm minus Pe. And finally, the rotor angle stability. It is the ability of the interconnected synchronous machines of a power system to maintain the synchronism. The stability problem involves the study of the electromechanical oscillations which is inherent in the power system. What are the different types of rotor angle stability? Small signal stability or steady state stability, and then transient stability. While considering voltage stability, it is the ability of a power system to maintain steady acceptable voltages at all the buses in the system under normal operating conditions and after being subjected to a disturbance. The major factor for the system to be slipping from the stability state to the unstable condition is the inability of the power system to meet the demand for reactive power. Midterm stability, it represents the transition between a short-term and the long-term responses. Short-term in the sense it is from 0 to 10 seconds. Midterm is 10 to few minutes and longer is a few minutes to tens of minutes. While considering the long-term stability, these problems are being associated with the inadequacies of the equipment responses, poor coordination of control and protection equipment, and insufficient active and reactive reserves. But they can be maintained for a better operation of the power system.